and welcome to this fourth lecture of the module on differentiation and integration. In the previous lecture what we were doing is we derived some of the integration formulae. These integration formulae were classified as Newton-Cotes integration methods, and the examples of Newton-Cotes integration formulae, the first one was the trapezoidal method, Simpson's 1/3 rule, and Simpson's 3/8 rule. Okay. What I will do today is derive the error equation for the Simpson's 1/3 rule. After going over the derivation for trapezoidal rule, Simpson's 1/3 and 3/8 rule, what we did was used Microsoft Excel to find integral from a to b. I think we did it from 1 to 2 if I am not mistaken, of 2 minus x plus ln x dx. That integration we did, and we used basically the trapezoidal method, the Simpson's 1/3 rule and the Simpson 3/8 rule, and we saw that when we used trapezoidal method with our h equal to 1, at that time there were significant errors between the actual integral value and the numerical integral value. Then when we chose h equal to 0.2, that means we split down the overall interval. So this is what we wanted to find out, this particular integral, or I believe the might have, the other line might have actually been closer to that. Okay, so we wanted to find this particular integral. What we did was first applied the trapezoidal rule directly to this integral, then we broke down this particular to this interval, then we broke down that interval into two intervals, and then we applied trapezoidal rule, and then we compared the results of the trapezoidal rule with the application of Simpson's 1/3 rule, and we saw that two applications of trapezoidal rule gives less accurate results than Simpson's one application of Simpson's 1/3 rule. Although the number of intervals that trapezoidal rule uses and Simpson's 1/3 rule uses are the same when we are going to break down the interval, integration into two intervals for trapezoidal rule. Next, what we did was we broke down the same, instead of two intervals we broke it down into three intervals, and found out the numerical approximation of the integration using the trapezoidal rules, applying trapezoidal rules 3 times, once for this interval, second and third time for this interval, h being 0.333. Then we applied Simpson's 3/8 rule for a single application of the 3/8 rule, which uses the point y1, y2, x1, x2, x3 and x4. And we saw again that the Simpson's 3/8 rule results were more accurate than the trapezoidal rule, and were indeed more accurate than the Simpson's 1/3 rule, but the difference between Simpson's 3/8 rule and the Simpson's 1/3 rule accuracy was not that significant. We will take another example in today's lecture, a more chemical engineering example if you will. We will take that example to demonstrate once again how one would use the trapezoidal or the Simpson's 1/3 rule. Before doing that, I will again derive the error equation for the Simpson's 1/3 rule in order to show how the Simpson's, why the Simpson's 1/3 rule is actually fairly popular. Okay, so the polynomial that we are going to fit in Simpson's 1/3 rule, what we said we are going to do is between the value a, we will call that as x1, a plus h will be x2, a plus 2h will be our x3, which is our b. Okay, so this is what we said we are going to do. So we are going to fit a polynomial to this this data, and then we are going to integrate the polynomial that we fit. Now if we were to not stop at a plus 2h but go ahead a plus 3h, a plus 4h and so on and so forth, we will get a higher order polynomial. So a general polynomial p is going to be using the forward difference formula is going to be y1 sorry plus alpha times delta y1 plus alpha square sorry not alpha squared, alpha minus 1 by delta squared y1 divided by 2 factorial plus alpha minus 1 alpha minus 2 divided by 3 factorial delta cubed y1 plus alpha minus 1 alpha minus 2 alpha minus 3 by 4 factorial into delta cubed y1 and so on. Okay. So this is what our polynomial is going to be. If what we did in the previous lecture is we said that since the polynomial is only going to be fitted to this 3 data points, we will just retain these 3 terms, and the terms that we are neglecting are the terms over here. So because we are neglecting all these terms, there will be certain error that is going to be associated with neglecting those terms, and then we try to find out what that error is going to be, so on and so forth. That is what we essentially that part of it we did not do. What we did was only retain this particular term. What I am going to show today is that in the Newton's 1/3 rule, in fact this term also disappears when we actually do the integration, and the leading term that that gets left is this term. This term is h to the power 4 accurate. So when you integrate it, it will get Newton's 1/3 rule as h to the power 5 accurate. So the Simpson's rule, if you recall from the previous lecture, was h cubed accurate, whereas the 1/3 rule is going to be h to the power 5 accurate rather than h to the power 4 accurate, and that is going to be a very important property of these Newton Cotes formulae that makes Simpson's 1/3 rule actually more popular than the Simpson's 3/8 rule. Okay. So because people have done this derivation and we know what to expect, that is why I am actually going to retain this particular term and essentially going to replace this term with the numerical with the mean value theorem, and that term when we replace with mean value theorem is going to be alpha minus 1 alpha minus 2 alpha minus 3 by 3 factorial multiplied by h to the power 4 f4 dash of zeta, where zeta is some point that lies between a and a plus 4h. Okay. So that is what we get, where alpha, if you recall, is defined as x minus x1 divided by h. Okay. So that is the definition of alpha, and therefore the definition of therefore when we differentiate this equation we will get dx is equal to h d alpha. Again this is something that we have done in the previous lecture. It is not something that that's new in this particular lecture. What we are actually going to do is see what happens when we apply the same methodology to the Simpson's 1/3 rule. Okay. So our integral I, the numerical integral I, is going to be integral from x1 to x3, which is h equal to 0 to h equal to 2, 0 to 2 y1 plus alpha delta y1 plus alpha minus 1 delta squared y1 by 2 plus alpha minus 1 alpha minus 2 by 3 factorial delta cubed y1 plus alpha minus 1 alpha minus 2 alpha minus 3 by 4 factorial h to the power 4 f4 dash. I will just write it a little bit, rewrite this. Okay. So, the next term after this is going to be plus alpha, alpha minus 1, alpha minus 2, alpha minus 3 by 4 factorial h to the power 4 multiplied by f 4 dash of y, sorry, f 4 dash of zeta. Okay. That is our polynomial that we had over here. I have written that polynomial, and integral of that polynomial with dx is what our I is, and dx is h d alpha. Okay. So, our dx was h d alpha. Remember what we want to do, our I is nothing but integral from x minus a divided by h, or sorry, a minus x1 divided by h to b minus x1 divided by h p dx, and dx is going to be replaced by h d alpha. So, we have where a is nothing but our x1, so this is 0, b is a plus 2h. So, so that is a plus 2h minus a, which is divided by h, which is 2. So, that is why we get 0 to 2 p multiplied by h d alpha. Again, this is something that we have done in the previous lecture. Okay. In the previous lecture, we had considered all these terms, and based on these terms we had obtained the integral of the integral I using the Simpson's 1/3 rule, and that particular result essentially gave us h divided by 3 y1 plus 4 y2 plus y3. Okay. That was the result that we derived in the previous lecture. Now, talking about this particular guy, we have integral from 0 to 2, this is alpha squared minus 2 alpha, sorry, minus 3 alpha plus 2. So, that is multiplied by alpha. So, alpha cube minus 3 times alpha squared plus 2 times alpha divided by 6, which is 3 factorial, multiplied by delta cubed y1 h d alpha is this particular guy, and this final term over here is going to be, we will write that as integral from 0 to 2, this is alpha multiplied by alpha squared minus 3 alpha, or this is going to be alpha cubed minus 3 alpha squared plus 2 alpha multiplied by alpha minus 3 divided by 24, and it is h to the power 5 f 4 dash zeta times d alpha. Okay. Now, we will just consider the term this particular term and do the integration, and when we do that we will get integral from 0 to 2, one will have basically delta cubed h delta cubed by 6 outside the integral sign, and we will have inside integral it is going to be alpha cubed d alpha minus 3 times integral alpha squared d alpha plus integral from 0 to 2 alpha d alpha, or actually 2 alpha d alpha, sorry. Okay. This is what we will get, that we will be able to write as h delta cubed y1 by 6. This is going to be alpha to the power 4 divided by 4 minus 3 alpha cubed divided by 3, which is just going to be alpha cubed, plus 2 alpha squared divided by 2, which is just alpha squared, going from 0 to 2, okay, which we will be able to write as h delta cubed y1 divided by 6 multiplied by alpha to the power 4 divided by 4, which is 2 to the power 4, that is 16 by 4, that is 4 minus 0. So it is 2 to the power 4 by 4 minus alpha cubed, which is 2 to the power 2 to the power 3 plus 2 squared. Okay. So this is 16 divided by 4, which is 4, this is 8 and this guy is 4. So here what we have is 4 minus 8 plus 4, that is 8 minus 8, that is 0. So this particular term has become 0. Okay. So what has happened is, when we retain an additional term in this integration, when we actually do the integration and substitute the values of the limits of integration into this particular equation, what we realize is that after integration this term drops out. Okay. So the error is not going to be governed by this particular term, but in order to figure out the error we have to include an additional term over here, and that particular additional term is essentially this term, and then we go ahead and do the integration of this term to indeed see that after doing the integration that particular term does not disappear. So what we will write is h to the power 5 f 4 dash of zeta divided by 24 multiplied by integral from 0 to 2. We have essentially alpha to the power 4 minus 3 alpha cubed plus 2 alpha squared minus 3 alpha cubed minus plus 9 alpha squared minus 6 alpha. D alpha. Okay. So 3 minus 3 alpha cubed minus 3 alpha cubed is going to be minus 6 alpha cubed. So I will write down over here, and plus 2 alpha squared plus 9 alpha squared is going to be plus 11 alpha squared, okay, minus 6 alpha d alpha. Okay, which is going to be equal to h to the power 5 24 divided by 24 alpha to the power 5 divided by 5 minus 6 alpha to the power 4 divided by 4 plus 11 alpha cubed by 3 minus 3 alpha squared from 0 to 2. Okay. So this guy is going to be 32 minus 0 divided by 5. So it is 32 by 5 minus 6 alpha to the power 4 by 4, alpha to the power 4 is 16, 16 divided by 4 is 4, 4 multiplied by 6 is 24. So minus 24 plus 11 by 3 alpha cubed, so that is going to be 88 by 3, and minus 3 times 4 is minus 12. Okay. So this is 32 396 by 5 plus 88 multiplied by 5, 8 5 is 40 and 8 times 5 is 40, 440 divided by 15 minus 36. So this is going to be 536, this guy 536 by 15 minus 36, and or it is going to be minus 36 multiplied by 15. So 15 6 times 6 is 90, 0 9 carried over, 45 54. Okay. So what we get is 36 minus 536 minus 540, that is minus 4 by 15. So we will have h to the power 5 f 4 dash of zeta divided by 24 multiplied by minus 4 by 15 this, and we get 6 over here, 15 times 6 is 90. So this is minus h to the power 5 divided by 90 f 4 dash of zeta. Okay. So this is the error in computing the integral using the Simpson's 1/3 rule. Okay. So the error in integral of Simpson's 1/3 rule is of the order of h to the power 5. If you recall from the previous lecture, error in in finding the integral using the trapezoidal rule was h to the power 3. Okay. So I will write those results down. Okay. This is something that we have not derived yet, I am just stating it as it is that the error in case of Simpson's 3/8 rule is order of h to the power 5. Okay. What happens in Simpson's 3/8 rule is that we will use this and this term, the 4 terms we will use to derive the 3/8 rule the way we talked about in the previous lecture, and this particular leading term will give us an indication of whether or not the error is h to the power 5 accurate or it is even more accurate than that. When we do the derivation for Simpson's 3/8 rule, we will find that this particular term does not disappear, this particular term also stays there. This term is h to the power 4, we will get another h factor because of dx equal to h d alpha. So we will have this particular term when we do the integration corresponding to h to the power 5. Okay. That term, because it does not drop out, as a result of that term we have the accuracy of the Simpson's 3/8 rule to be h to the power 5. Okay. So the trapezoidal rule is h cubed accurate, Simpson's 1/3 rule is h to the power 5 accurate, Simpson's 3/8 rule is again h to the power 5 accurate. This uses 2 intervals, so this is, I will call this NC2, Newton Cotes formulae with 2 intervals. Simpson's 1/3 we can call NC3, Simpson's 3/8 we can call NC4. What we will do is go to Excel and do one chemical engineering problem of interest, and the problem that we will do here is going to be design of a plug flow reactor. So we will solve PFR design equation. Okay. The design equation for plug flow reactor, so what we talk about in plug flow reactor is we have the flow coming in with a velocity of f naught, the overall the volumetric flow rate f naught, the overall volume of PFR is going to be V. Some reaction takes place, let's call that as A going to B, that is the reaction taking place within the system, and let us say rate minus RA is some K times Ca to the power say 1.2 or say 1.25 arbitrary numbers. Okay. So this is, let us say, the rate of reaction taking place in the PFR. We have the flow rate coming in at F0, initial concentration of of the overall initial concentration of the species, let us say, is Ca0. So then the equation is f v by f0 is going to be Ca0 integral from 0 to x exit dx by minus Rx, okay, where R is really the rate of reaction. Okay. This is the expression that we get for doing this to find the volume of the PFR that will give a desired exit concentration. Okay. So let us say that we want to find the volume of the reactor that gives 90% conversion. That means x at the exit is going to be 90% or 0.9. So the problem that we have is V by F naught equal to Ca naught dx by minus Ra. Let us assume that Ca naught, we will just use some arbitrary data. Ca naught is 1 moles per meter cubed. Let us say we want to find out the volume. Let us say the flow rate F naught is say 10 meter cubed. Okay. This is the overall data that is actually given to us. The rate of reaction is R equal to K Ca to the power 1.25, and Ca, the way it is related to the conversion is so conversion is Ca naught minus Ca divided by Ca naught. Okay. So Ca is going to be Ca naught multiplied by 1 minus conversion. Okay. That comes essentially from definition of conversion, which is Ca naught minus Ca divided by Ca0. So you multiply Ca0 over here, so you will get Ca naught x equal to Ca naught minus Ca, or Ca equal to Ca naught minus Ca naught x, which is essentially this. Substituting the value of Ca naught equal to 1 in this particular equation, Ca is going to be 1 minus x. Okay. And therefore R minus Ra is going to be K times 1 minus x to the power 1.25. Okay. And when we substitute this particular equation into this and we substitute all the values over here, we will get V divided by F0, which is 10, equal to Ca naught, which is 1, multiplied by dx divided by minus Ra, and minus Ra is going to be K times 1 minus x to the power 1.25. Okay. We will take 10 on to the other side, so we will get V equal to 10 times integral from 0 to 0.9 dx divided by K 1 minus x to the power 1.25, and let us arbitrarily take the value of K as 5. So we will substitute that value also over here as this. Okay. So the integral that we are interested in finding is V equal to 2 multiplied by integral from 0 to 0.9 dx divided by 1 minus x to the power 1.25. So that is the problem that we are going to try to solve using various numerical integration techniques using Microsoft Excel. So what we want to do is I equal to integral from 0 to 0.9 f of x dx. That is the integral that we want to find. F of x, where x is the conversion, as we have written on the board, f of x is going to be 2. So because we get 10 divided by 5, that gives us 2. divided by 1 minus x to the power 1.25, that is going to be our f of x, okay, and we want our x to go from 0 to 9. Okay. So, our integral I is nothing but the total volume. So, let us write down the x value, and we are going to start with x equal to 0, and we also need to decide what our h is going to be. H, let us say, is going to be equal to 0.9. Okay. So, our x is going to be equal to the previous value plus the h, and we do f2 and put dollar signs over there, so that when we drag it the value does not change. Okay. Then we compute f of x. F of x is going to be equal to 2 divided by 1 minus x to the power 1.25. Okay. And we just go and drag this. So, this is the value of f of x at x equal to 0.9, and this is the value of f of x at x equal to 2. Okay. And our volume is going to be just the final integral at x equal to 0.9. So, using the trapezoidal rule, it is going to be equal to our h divided by 2, that is this value, we will put the dollar signs over there, divided by 2 multiplied by y1 plus y2, that is going to be our integral. Okay. So, the volume of the reactor that is required obtained from the trapezoidal rule, application of the trapezoidal rule only once, is going to be 16.9. Okay. Instead of that, if we were to apply the trapezoidal rule twice, we will get a better value of the integral. Okay. So, what I will do is volume required, and I will write down the values from the trapezoidal rule, then the Simpson's 1/3 rule and the Simpson's 3/8 rule. I will just copy this and do paste special and just copy the value over there. Okay. This is h equal to 0.9, or single application, 2 applications and 10 applications of the rules. Okay. Now, if we were to use 2 applications of the rules, our h is going to be 0.45, okay, and we just have to drag it once, drag this once, drag this, okay, and if we do f1, we will get the appropriate value. If we do f2, again we will get this appropriate value, and our total volume is going to be equal to this plus this. So, total volume is going to be equal to this guy plus the next guy. Okay. So, the volume that we get on 2 applications of this of the trapezoidal rule is going to be as shown over here, 10.352. Now, let us say we want to do 10 applications, then we will go for h equal to 0.09, okay, and we just copy this down 10 times, okay, and then we just have to sum over all of this. Okay, not this guy. Okay, and the 10 applications are giving us the value of the volume that is obtained as 6.5025. So, what we are seeing over here is as the number of applications of the trapezoidal rule are increasing, the value keeps decreasing. Okay. Let us do 20 iterations. So, that is going to be equal to 0.9 divided by 20, okay. And when we do that, we will have to just drag this further, okay, and we will have to just double click this, and this is going to be just the summation for this entire range. Okay. So, as you can see that with 20 applications, the value of the volume is now beginning to converge. Okay. Let us do 50 applications now, okay, and H then is going to be equal to 0.9 divided by 50, okay, and we just drag this for many more cells, so that we reach 0.9. Okay, go up and double click this, go up, double click this, go to the last value, delete the last value, and we find the volume as the sum of the entire number of intervals that we have obtained, okay, and the volume that we get is 6.238. So, what we see is that finally it seems the method seems to be converging. What we need to do is we need to define our error value, and we need to use large enough number of intervals such that this particular method finally converges to the final volume that we are interested in. Okay. It is the same idea that was used in checking the convergence of the various methods that we will use over here as well. I will just write this alignment merge and center aligned, and I will write this as trapezoidal method. Okay. Next, what I will do is use Simpson's 1/3 rule in order to get this particular, to solve this same problem. Okay. And again we will use H equal to 0.9 divided by 2. Okay. Keep in mind that in application of the 1/3 rule we will have to use in application of 1/3 rule we will have to use even number of intervals. In trapezoidal rule the number of intervals did not matter. Okay. We will again have f of x, sorry, we will have again x, f of x integral and then the total volume using the 1/3 rule. We will start off with 0, and as it was here we will just copy this and then just move this guy over here. Okay. And this should be good, our f x. I will just copy this, I will just move this over here. Okay. So, the Simpson's 1/3 rule, the integral was, so in the trapezoidal rule the integral was nothing but h by 2 multiplied by y1 plus y2. In this case the integral is going to be equal to h divided by 3. So, I will put the dollars because h is not changing, divided by 3 multiplied by y1 is this guy plus 4 multiplied by y2 plus y3, that is the integral, and the volume is nothing but just this particular value. Okay. So, the volume that we are getting from the single application of Simpson's 1/3 rule is 8.17 approximately. Okay. I will just paste it over here. Okay. Now, two applications of the Simpson's 1/3 rule means once we will apply it from 0 to 0.45 and the second time we will apply from 0.45 to 0.9. So, we are going to divide this by 4 this time and we will apply this. Okay. And then integral again we have to compute between 0.45 and 0.9, right. So, what we need to do is y1 plus 4y2 plus y3 multiplied by h by 3. Okay. So, this is what we need to do, and the volume that is to be computed is going to be this entire sum over here. Okay. So, two applications of Simpson's 1/3 rule give us a volume of 6.71. Okay. And 10 applications we will have to divide this by 20. So, the 10 applications will actually give us let us just see what we will get. Just keep pasting. Okay. Okay. So, this is going to be y1 plus 4y2 plus y3 multiplied by h by 3. This is all going to use then these 3 points, this will use these 3 points, so on and so forth, and the volume is going to be the entire sum that we just need to go and drag it over here, and the volume that we get is 6.23 using 10 applications. Okay. This is already quite close to the 50 applications of the trapezoidal rule. So, just 10 applications of the Simpson's 1/3 rule are going to come very close to 30 applications of 50 applications of the Simpsons of the trapezoidal rule, and we will just go and solve this for the Simpson's 3/8 rule. Okay. And in 3/8 rule the h has to be the single application, for single application h has to be equal to 1/3 of the total value, and we will just be able to copy these guys over here for the 3/8 rule. I will just increase the size. Okay. And integral has to be equal to the h that we use is going to be here. Okay. So, x will be x0 plus this h, and we will just drag this over here, f2, this is correct, we will just drag this. Integral is going to be 3 multiplied by h divided by 8 multiplied by y1 plus 3 y2 plus 3 times y3 plus y4. Okay. And the volume is just going to be equal to the integral for this particular case. So, we just copy this volume and paste it over here. Okay. And now we do two applications of the Simpson's 3/8 rule. the two applications of the Simpson's 3/8 rule. Will lead us to the volume equal to almost 6.5. Okay, and for 10 applications of Simpson's 3/8 rule, we just have to use h equal to 0.03. And just drag this and then copy. We have to skip 2 cells and paste 1, 2 cells are skipped and then paste 1, 2 cells are skipped and then paste again, and these values we do not need, and this guy is going to be sum of this entire structure. Okay. And as you can see that with 10 applications, the volume that we get is approximately 6.23. Okay. So, this is the volume that we will get with single application of the trapezoidal rule, 2 applications of the trapezoidal rule. Even with 10 applications of the trapezoidal rule, we find that the actual value is fairly far away from the value of the actual volume that will be needed. So, we actually need to go to 50 or maybe 70 applications of the Simpson's of the trapezoidal rule in order to get the actual value, whereas with respect to the Simpson's 1/3 rule will perhaps need about 20 applications, and with the Simpsons or maybe 25 applications. For the Simpson's 3/8 rule will perhaps need something like 15 applications. 15 applications of the Simpson's 3/8 rule require about 45 data points, whereas 20 applications of the Simpson's 1/3 rule require 40 data points. So, that is the amount of effort, how the overall effort in this particular case scales. Okay. So, to recap, what we have done so far is we have considered the trapezoidal rule, Simpson's 1/3 rule and the Simpson's 3/8 rule, did the derivation of the trapezoidal rule using multiple methods. The first method that we used was a geometric method, the second method that we used was fitting a straight line to the data points, and the third method that we used was using the Newton's forward difference formula. Then we expanded the Newton's forward difference formula to take care of Simpson's 1/3 and the 3/8 rules. Then we considered a simple example of f of x equal to 2 minus x plus ln x integral from 1 to 2 of that particular expression, and we compared Simpson's 1/3, 3/8 and the trapezoidal rule using that method. And today what we have done is shown that the errors in the 1/3 rule scale very nicely compared to the trapezoidal rule. Specifically, the errors in the Simpson's 1/3 rule are h to the power 5 order of magnitude, whereas for the 1/3 rule is for the trapezoidal rule is h to the power 3 order of magnitude. And then finally, we took a chemical engineering example, a real life example of interest to us as chemical engineers, and showed where the numerical integration can be actually applied. What we have done finally to figure out how many intervals are needed is what is known as some kind of a grid independence test. What we need to do with respect to any numerical method, any integration or ODE solving method that we are going to use is use a number of intervals and go to a large number of intervals, so that the results do not change by changing the number of intervals any further. As we saw in the 1/3 rule, going from 10 intervals to 20 intervals still improved the volume that we get using this the Simpson's rules. Okay. As a result of this, we have to use a large number of iterations. Okay. And just to finish off, I will just go once again to the board and show you why exactly we require a large number of iterations in this particular example that we have taken to finish off this example. Okay. So, our f of x was 2 divided by 1 minus x to the power 1.25, 2 divided by 1 minus x to the power 1.25. Okay. If we plot this particular curve, okay, of going from x equal to 0 to x equal to 0.9, at x equal to 0 this value is approximately equal to 2, not approximately, at x equal to 0 this value is exactly equal to 2, okay, and at x equal to 1 this particular value is essentially going to be infinity. Okay. So, the curve, the way the curve looks is going to be somewhat like this. Okay. What we are interested in when we say we want to find the volume of the PFR, what we are interested in doing is to find the area under the curve going from x equal to 0 to x equal to 0.9. This is the curve that we are interested in. This is the area that we are interested in. Okay. When we use a single application of the trapezoidal rule, I will show that with a yellow color chalk. When we use a single application of the trapezoidal rule, we are connecting these 2 points with this yellow line, and we are approximating this integral as this particular area. As a result, there are significant errors that we get using the trapezoidal rule. Now, two applications of trapezoidal rule means that we consider a data point 0.45 at 0.45, which is essentially this guy. So, two applications of trapezoidal rule are going to be area under this, the new yellow curve. Okay. So, this is going to be the area that we will get as the numerical approximation of the actual volume using the trapezoidal rule. And so, this area under this yellow curve, there are significant errors associated with it. Again, as a result, when we had two implementations of the trapezoidal rule, there were significant errors. Now, when we are going to use the Simpson's 1/3 rule, what we are doing is we are trying to pass a second order curve through these 3 points. A second order curve through these 3 points may perhaps look somewhat like this. Okay. So, it is again it is not following the White curve perfectly, but perhaps it will do a better job, or not perhaps, usually it will definitely do a better job than connecting just three of these data points with straight lines. As a result, the yellow area that I am showing as hatched line with a single application of the trapezoidal single applications of the Simpson's 1/3 rule, that itself is significantly better than two applications of the 1/3 rule of the trapezoidal rule. Okay. So, that is the reason why we get a significantly better performance when we apply, that is a geometric interpretation why we get the significantly better performance when we apply the 1/3 rule rather than two applications of the trapezoidal rule. Okay. And numerically speaking, why we get such a better behavior is that the trapezoidal rule is order of h to the power 3 accurate, and the 1/3 rule is order of h to the power 5 accurate. Okay. So, this is where we finish this particular lecture in this module, the 4th lecture in module 6. In the next lecture, we will cover one more interesting method and one more way of actually deriving the integration formula for the trapezoidal rule. That is what we will cover in the next lecture and finish off this particular module in the next lecture. Thanks.